In this problem, we're given the following circuit diagram. We need to find the Thévenin equivalent circuit with respect to the terminals A and B for the circuit. Our terminals are going to be right here, A and B, and we need to find the voltage of A and B. We also need to find the resistance of A and B because this is the Thévenin equivalent. The reason why we need voltage and resistance is because the Thévenin equivalent of this would be a voltage right here. This would be VTH plus minus, and then we would have a resistor right here. This would be our RT of H, and then we would have our node A, and then we would have our node B, or I'm sorry, terminals A and B right here. That's the actual kind of form for it. With that in mind, we can solve this problem. First thing I'm going to do is find resistance because I find it easiest. If we look at this 8 ohm resistor and this 12 ohm resistor, we can see that they are both going to be in parallel to this 5.2 ohm resistor. So we can combine the series and parallel formulas together. For the parallel formulas, we need to do this first. We're going to have 1 over our first resistor plus 1 over our second resistor, and this is all raised to the negative first power, and then 5.2 is in series with it, so we're going to add this. If we do this, we're going to get 10. Now we have 10 ohms of resistance here. We also have a 30 ohm resistor right here. Our 30 ohm resistor and our 5.2 ohm resistor are in parallel. We can see this if we draw a current this way. Some of it's going to go this way, and the rest of it is also going to go this way. So they are in parallel. We have to find the resistance once we combine them. So we're going to do that again down here. Again with the parallel formula, we're going to have a 1 over 10 plus a 1 over 30, and this is being raised to the negative first power, and we're setting this equal to 7.5. Since we've calculated all the resistance, this is the resistance for our A and B basically, or our Thévenin resistance, this part right here, and we can write that our RTH is equal to 7.5 ohms. That's how you would solve the first part of this problem, or technically the second part. But now we're going to go and find our VT of H. So I'm going to erase all of the marks that we did in here so we can start fresh. And looking at this, to find VT of H, well, VT of H is basically going to be right here. And our resistance is this that we found right here. So we know that this is our voltage that we need to find. Well, if we look at this, we can kind of do a node voltage analysis. If we see this, we have our node 1, and we have our node 2 here. So we can set this equal to our V1 with a plus minus, and then we can have another plus minus and say this is equal to our V2. And we can say that our V2 is equal to our VT of H. And now we're just going to do the node voltage method, and that is found in chapter 4.2. To start this off, we are going to have a V1 minus our voltage source. So we're looking at our first node. We're going to say that our V1 minus our voltage source, which is 500 volts, because the 500 volts is coming into this node. That's why it's minus, and then this is happening all over the 8 ohm resistor. Next, we're going to look at the 12 ohm resistor. It's going out of our node, so we know it's a plus. Remember, if something's going into a node, it's negative. If something's going out of a node, it's positive, and this is just Kirchhoff's current laws. We're going to have a V1 over 12 ohms of resistance, and lastly, we are going to have our plus V1 minus V2, and this is all happening over our 5.2 ohm resistor. By the law, we set it equal to 0. We can simplify this a little bit. I'm going to combine all of the V1s, so I'll have V1 on the outside, and then inside we'll have 1 over 8, and this will be a plus 1 over 12, and the next one is plus 1 over 52, or I'm sorry, 1 over 5.2, should make that decimal a little bit more clear, and this is all in a parenthesis, and we can set 1 over ohms on the outside. That's the units for it. Now we're going to look at the constant because we have this 500 voltage over this 8 ohm resistor. If we divide these, we're going to get a minus 62.5 amps, and then lastly we are going to have a minus V2 over 5.2, and this is all equal to 0. We can simplify this a little bit. After we do that, we are going to get this for our first equation. We notice we have another unknown here, and this is our V2, so now we are going to solve for our V2. I'm going to do this in gray just so we get the colors correct, And for our V2, we know that we have some voltage coming in this way. We're going to have a V2 minus our V1, and this is taking place all over the 5.2 ohms of resistance. Next, we would normally have some current or voltage coming up this way, but we don't here. We should remember that. And if we look up though, we actually have a current and a voltage coming this way. We have over this 30 ohm resistor right here, 500 volts coming in. If we look at this, we can see that our 500 volts is coming this way into the 30 ohm resistor and then across here. However, it's not exactly 500 volts. So when we add this in here, we're going to say that we have a V2 minus 500, and this is happening over the 30 ohm resistor. Lastly, the only thing else that's connected here is this 10 amps. This 10 amps is going into our node, so it's also a negative. We're going to have a minus 10 amps, and because of Kirchhoff's voltage law, this is equal to 0. Now we're going to do the same thing that we did for the first one. We're going to separate everything. We're going to have our V2 right here, and then inside of this we have a 1.5.2, and then we have a plus 1 over 30, and then we are going to have 1 over ohms on the outside for units. Next, we have to deal with our V1. We have a minus 1 over 5.2 ohms times V1, and then we have two constants. We have this minus 500, which should be minus 500 over 30, but I'm just going to say 50 over 3, getting rid of the 0 amps, minus 10 amps is equal to 0. Now I'm just going to factor out some things and combine like terms. And then from here, we are going to get our second equation. We can put this in a matrix calculator. I'm going to substitute our V1 for an X. So say V1 is equal to X and V2 to be equal to Y when we do this. It's very important to note this. And I'm plugging this into a Symbolab matrix calculator. It will be linked below. So I plugged everything in. This is the first part. This is our 0.40, and this is our negative 0.192. V1 and then V2 is plugged in, and then I have our X here and then the Y down there for V1 and V2. And this is our second equation where we have a negative 0.192 for our V1 and then a 0.226 for our V2. These are written backwards in the notes right here, or in the problem solving right here. This should be in the V1's place. If we were to reorganize this V1 would be out front, and then this V2 would be right here. And then this is equal to 62.5 and 26.67. When we do this, we're going to see that our Y is 56.67 over 0.13384. If we plug this into a calculator, we're going to get the result 423. So our answer for our VT of H is 423 volts approximately. That's how you do this problem. If you have any questions about the material we covered, you can leave them in the comments below. If you want more problems like this, Introduction to Circuit Analysis, there will be a playlist link below, as well as notes to help do all of this stuff and study for any other material related to Intro to Circuit Analysis.